developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
Historically, new recipes for integrating advanced technologies into high-stakes domains have had a poor or mixed track record. Many promising technologies in the lab actually never get to be used in operations or have really surprising negative consequences. Being able to build a test kitchen that will simulate and help us understand better how they'll transition into real-world operations are likely to positively impact SSA in real-world operations. We have two goals in our project. One, to evaluate multiple recipes for integrating advanced technologies into SSA operations, and two, to develop a repeatable method for Air Force and Space Force operations to use in evaluating the impacts of future innovative technologies. In this first 6-month increment, we will be focusing on stocking our test kitchen with the ingredients and the equipment necessary to discover new human technology recipes.
The centerpiece of our test bed is a method called Joint Activity Testing, or JAT, which was developed at Ohio State specifically to evaluate how advanced technologies like AI are likely to impact real-world operations. The goal of JAT is to empirically evaluate how the performance of people and technology together changes as a variety of different challenges increase. To do this, we will conduct a human-in-the-loop experiment and graph the performance of the human-machine system relative to the challenge or the difficulty of the scenario. We will then select a set of testing cases which cover a wide range of challenges and collect performance data across this range. We can then fit a statistical model of performance and use this model to compare the strengths and weaknesses among multiple different human-machine teaming strategies. In this example, although people with technology A appear to perform slightly better than people with technology B in the easiest scenarios at the left side of the graph, people with technology A performed much worse than those with technology B at the right side of the graph. Perhaps this collapse of performance we've observed with people using technology A is enough to justify us choosing technology B. Or perhaps we might use this graph to further direct research and development towards improving technology A at the right side of the graph.
Activities in space are important. Indeed, they are vital to our daily lives. Navigational devices, communication and transportation systems, and even much of our entertainment rely upon satellites in space. The mission for SSA operations is to ensure the safety of space vehicles performing these functions and to identify and resolve problems such as potential collisions or lost satellites. As the space environment gets busier and satellites get further and further away from Earth, operators will need new tools to handle the increased traffic and the complexity of future space operations. With advancements in technologies, new AI systems are being developed all the time, but little is known how to leverage these technologies for SSA. The Air Force and the Space Force will need to develop recipes for success, if you will, and a workforce ready to design and evaluate the technologies of tomorrow.
The results for our first 6-month increment are an experimental design which we plan to utilize in our next increment. We are focusing this experiment on one early decision which is central to most other space situation awareness activities: determining whether a detected satellite is actively maneuvering or passively station keeping. Participants will complete a sequence of scenarios. For each scenario, participants will be presented with a historical trajectory of satellite detections. They will be asked to report how confident they are that the satellite is actively maneuvering or station keeping. Each scenario will be progressed through multiple different points in time, and participants will be asked the same questions at every increment. This allows us to analyze how participants' understanding of the satellite evolves over time as they accumulate more data. Our experimental manipulations are informed by a set of guidelines we have synthesized at Ohio State, which are centered around supporting various aspects of joint human-machine activity. In designing machine aid to help participants make decisions about satellites, we focused on testing different degrees of technology assertiveness and transparency. Furthermore, we will test the impacts of additional contextual information and how that information might help participants recognize when machine recommendations are erroneous. In our experimental design, we operationalize these guidelines by varying the format of the machine recommendation. Sometimes no recommendation will be shown to the participants. Sometimes the machine will give a categorical recommendation, and sometimes the machine will give a recommendation with a continuous confidence value. Additionally, participants will sometimes be given additional context, for instance, an intel report of debris in the area, which may or may not impact how participants' expectations about the reliability of data or typical satellite maneuvers. Each participant will use each of the 3x2 experimental conditions. At minimum, measures of participant performance will include the speed and accuracy of decisions in each scenario. Challenge measures will include at least the amount of data available, the correctness of machine recommendations, and the correctness of the additional context provided. Through this experiment, we will be able to apply the joint activity testing methodology to space situation awareness operations.